like I said, the two things are going to be constraints and kinematics, and I'll do constraints first. So far, we've talked about, in terms of controlling objects, we've looked at keyframes, we've looked at connecting values between objects. What constraints do is let you control properties in a slightly different way. So the first one we're going to look at is called simply an aim constraint, which pretty much does what it says. So I want to make a cone because it's easier to see, and make a second object, right? So before we've talked about, I can connect this, I can parent this one to that one, or I can make a property of this one control that one. But what if you simply said, I'm wanting to control the rotations of this object, but what I want you to do is to look at this guy, right? So no matter where I move this object around the screen, point at it, right? So the way you do that, it's all under the animation menu, and you can't see it on mine, but there's actually a whole menu up here called constraints. And there's a lot of them. I'll run through a couple of useful ones for you. But for us, aim is probably going to be the most useful right now. So what I'm going to do is I'm going to pick the target, hold shift, and then pick the aiming object. Then I'm going to go under constraints and then aim, but be sure to click on the sort of box out here, right? So with all the sort of options in Maya that have this little white box, it means there's a set of options you need to input to the command. If you don't do this, it's basically just going to remember whatever you had last time for those things. So when I click on this, you get the aim constraint options. So the most important thing to know on this set of options, the aim vector and the up vector. Up vector, actually, you probably won't ever change unless you flipped your Maya to be Z up instead of Y up. Like I said, everything you see from me will always be Y up. That's saying Y up, so if you're thinking about it as a vector, so 0, 1, 0 is up, and Y if you figure X, Y, Z. The most important one is actually this, so the aim vector. So 1, 0, 0, if you figure X, Y, Z. Basically what that means is what axes do you want to aim at the object, right? So right now, I would be aiming the X-axis of the cone at the box, right? Then at the bottom, again, that's all, don't really mess with it. And then there's just a question of whether you want to constrain all the axes or just one. So we're going to stick with all for a second. And now, it's looking at it. But it's kind of hard to see because it's not really the one we want, right? I want it to actually point at it. So to do that, again, I'm going to pick my target, then pick the aiming, go constrain, aim, and I want it to be the Y, right? So Y is up from the cone. So to do that, I'm just going to say 0, 1, 0. Yep. If I wanted it to be the Z, I would say 0, 0, 1. And I'm going to add that. Right? So no matter where I go, it's always going to point at the object, right? Make sense? So what's interesting also with constraints is once you make them, and like everything else in Maya, you can always kind of either adjust their properties afterwards or combine them together, or lots of things. So when I pick my cone, if you scroll down, you can see it made under the shape this pcone 1 aim constraint 1. And the main thing here is this also has the name of this object, which is p cube 1, and then w0, and there's a 1. And the 1 basically means you can have the constraint. It's not necessarily an on or an off. It's always a sort of degree, with 1 being the maximum, right? So on the other hand, if I hit it now, if I just turn this to 0, when I move this guy, nothing. Right? So it's like you embed the potential in it, but you can always just turn it on and off. Right? So at any point, if I go over here, and if I turn it back on,
what would the number 2 mean by that? If you really think of it?
2's nothing over 1 does anything more than 1. It's a 0 to 1. You can do 0.5. You can do other things. So where that also becomes apparent is, let's say I also had this sphere. And the kind of interesting thing of constraints, when we looked at expressions and things, it's kind of like once you connect it to one thing, that's kind of it, right? It's hard to get 2 different objects to affect it. But let's say I already have this constraint happening, and I add this one. So I go from pick the sphere, pick the cone, and I go constrain aim, same thing with the y. It doesn't override it, it just averages the 2 of them together, right? So it's always going to point at the exact midpoint of these 2 objects. You can keep adding those all day. And then again, if you go back to the cone, you can see there's both of these down in here, right? So now, if I turn this one to 0, it's only going to follow this guy. So it's not affecting it. Again, the behavior's there, but it's just turned off. Turn it back to 1. So that's exactly the midpoint. Like if you wanted to pull it more to this one, come on. So now they both have an even weight. If I reduce this one to say like 0.5, it's going to pull proportionally more to the cube, right? So there's really no limit. I mean, you can set up a sort of system where it has an embedded aim constraint to everything, and then you just kind of turn them on and off. What's important to understand too is, let's say you had this sort of situation where at one point over time, you want it to point at one or the other. Well, since this is just a value like anything else, I mean, you can also control it like you would anything else. So we could say, let's say if I flip them both to 0, and at frame 1, I'm going to key it. Then let's say obviously at frame 20. If I did it this way, so then at frame 20, set it to 1. Keyed it. It's hard to see it because it's so fast, but all right, that's a little too fast. So. So let's say I wanted it to kind of smooth over to it. Still too fast. So the thing is here, anytime it's getting above 0, it's automatically flipping it. So what needs to happen, so I don't want it to happen until 20. Is where is it? So by picking it and just changing the tangent, it means that it's going to stay 0 and then at 20 flip on, right? So because before it was actually going to, because we know anything it gets over 1, it's like clicking it on, and we want it to not kind of flip the switch till 20. So it's just about picking the key and changing the tangent. So now, nothing, nothing, nothing. Oh, no, it's going to be 100. So, sorry, I moved the key to 100. So then anything that happens after 100, it's then being controlled here. I mean, the point of that is, it's just a different way of thinking about how you control the objects, right? It's not necessarily, you're not necessarily animating the rotations directly. You're just embedding the behaviors and saying, okay, at frame 200, from frame like 100 to 200, follow this thing. From frame 200 to 300, follow this thing. So you're actually animating the translate of a second object, which is controlling the rotation of the other one, right? But with servos, it gets kind of useful because it's, if you think about it, if you're needing to kind of target something specifically, you can deal with moving the object and just say, look at this object or point at the center of that object. So, just so you know, I'll show you a couple more. That's probably the most useful of the constraints for what we were doing. You can also, there's a lot of other things you can do with it. One kind of fairly useful thing you can look at too. And the question came last time, what is the soft selection? Right, so I have a polysurface, and normally I could either just pull a vertex or pull the surface. Soft selection lets you kind of start from a point and then create a fall off. So if I pick it and then go to the attribute editor, it has the radius, even the curve on how it falls off. See if you want to. It's a sweet little tool. It's very simple, but it's a very nice little tool. So, also again, just to that's the problem with the stupid self-selection is once you have it on, if you forget to turn it back off, it keeps trying to add them. So you have to go back to your normal selection. And right? So it's kind of fun. So in the same way, just to prove a point, everything is dynamic and everything is animatable, right? So if you wanted to if I said, I need you to make an animation of this thing warping, you set up the handle, and then all you literally have to do is, we're on frame 1, should I get some more frames? So soft mod, right click on it, set key. right? Again, animating one number. And that's how this whole kind of system works. Is the beauty of doing this fact that it's an animation software is, there's a lot of just vector math and matrix math happening in the background, but the kind of target audience for this stuff doesn't really care. It's more about just making the tools, right? You want to be like, here's a tool, change the number, does it look right? There you go. So to build on that for a second, this is a little bit of a side note, but good for you to know. I want to go back to my friend the cone. More like a spike. So another really simple one is I'm going to pick the plane, pick the cone, and under constraints, I'm going to say geometry. Now, the problem is here that it constrained it based on its pivot point. So I'm going to undo that for a second. So obviously if I pick the cone and I go to move it, you can see its pivot points here. For the sake of this right now, I'm just going to kind of half-ass moving the pivot. So on Mac, it's function home or function left arrow key. On Windows, it's the insert key. And now, you can see I'm moving the pivot point rather than and I'm going to, there's ways around it, but I'm just going to kind of eyeball it right now, because that's close enough. So,
you assign multiple pivot points to an object?
No, you cannot. The way you can kind of fake having multiple pivot points of an object is you group it to itself, right? So if you normally think about a group, you think, okay, it needs multiple things. So if I just pick the one object and just say, like, Control G to group it. So group 1 and pcone 1. So you can, that's the kind of closest cheat you can ever get to, right? So if you want it to rotate around here, you move the group. If you want it to rotate around here, you do it from the cone.
Can you animate them both?
Yeah. It doesn't always work, but it's kind of it's the best trick there is. All right, so now I'm going to go back to, I'm going to pick the surface, pick the cone, and I want to say geometry. And as I move, right, so it's really simple. It just means geometry constraint only controls translate. It doesn't control anything about rotation. But say now I can only move this cone on the geometry. If I want to add one more to that, which is usually what you do, you can pick this, pick that one again, because this is the controller and the controlled. So we're going to say constrain, then normal, make sure this is right. So the aim vector, we actually want to be y. So 0, 1, 0, and add it. So now not only normal, if you know, surface normal just means the sort of opposite of tangent, right? So whatever is kind of perpendicular to the surface at that point. So now if I move this guy around, oops. Right?
Right.
It really does. So. Yeah. So again, if you think about it, at the end of the day, here we're controlling a few different things. the translation, like the position, the translate XYZ of a cone, the rotation XYZ of a cone, but we're doing it by animating the fall off radius of a soft modification handle, right? So there's one input to the system, that's it. And the everything is just letting the kind of powerful but really simple calculation nodes compute the rest for you. And that's probably enough of a constraint for right now. So the other thing I want to show is kinematics. So if you've ever watched any sort of making of any film, so if you say like okay, this way, so say that's good. Right, so basically any animated character you've ever seen in a movie, game, whatever, is all pretty much animated this way, right? So if you think about it, characters, and especially you think about film, where it's like super, super high res meshes, what they're actually doing is deforming, even to render time, like millions of points at once, right? So if you think about a human mesh, it can be tens of thousands, if not millions of points. You don't want to inform a million points, right? You don't want to say, okay, this is your position, this is your position, your position. So you build a skeleton, right? Which is obviously built off the same idea is how people get animated, right? So we have the kind of more rigid bits that move around the squishy stuff, which is, your biology lesson for the day. The meaning of life, rigid stuff moving around the squishy stuff. But that's how we work, right? So there's lots of muscle, skin, fat, whatever gets moved, but it's the simple bones, right? So what you do is you can design what are called in animation world a character rig that is kind of, it's like it's given a relationship to the mesh and deform it in a certain way. So if you think in the sort of game or film world, there's people who their only job is they just make character rigs, right? Because the people, a lot of times in films, the people who then animate the characters, some of them, come from a background of not even knowing anything about computers. They just know how to animate. So, the way the business works is one team of people is making a mesh, another kind of group creates the kinematics and this sort of interface to the kinematics, and they physically hand it off to somebody else who then animates it, right? So you don't really, in the sort of professional setting, you would never get to make the whole, you wouldn't model the thing, make the rig and animate it. Like on any sort of scale, it would never happen. So it's an interesting thing because it's actually like an interface problem, right? So basically what these people do is they make an interface to the character. You probably didn't actually need any of that information, but it's good things to know about the world you live in. So the way, when you think about kinematics, right, you have to think about and your arm is like the easiest way to think of it, right? So if I was a digital character, right, and what I wanted to do was I wanted to animate my hand going to here, right? What happens with the kinematic chains, it's kind of like with the parenting. So this is it's kind of a graphic representation of the hierarchy as you would when you just parent, or like folders, right? So if you have like a main folder that has a folder that has a group of folders in it, that has another group of folders in it, all IK chains is a visual representation of that hierarchy. So you can, it's harder to see it here, but we'll show it when you start drawing it. So generally you have a central root on a character kind of torso, right? So kind of middle of a person. It then splits up. It might be the center of the shoulders split out, and then shoulder goes to elbow, elbow goes to wrist, wrist goes to finger, right? So in forward kinematics, if you wanted to say move a hand to here, you have to kind of start at the top of the hierarchy, right? So you would say, like, if I was animating me, I would say, rotate shoulder 25 degrees, rotate elbow 30 degrees, and then that would get it there, right? So it's going forward down the kinematic chain. Inverse kinematics goes in the opposite direction, not surprisingly. So what happens is you make control handles. So instead of like saying rotate shoulder, rotate arm, you just literally put a handle on the wrist, move the handle, and everything up the chain responds, right? So you just move the point, and it targets the chain to wherever you want to get to. So, how do we do that? You'll find it within the animation menu. You can also find it just on the animation tab here. I'm going to give you the kind of general overview of it. It's a big set of tools that you don't really need to know a lot of, but is interesting nonetheless. So this is the joint tool. So if I pick that, I get my crosshairs, and I'm just going to start clicking. So there's 1, 2, 3, 4, 5. Right? And if I look at the object over here, like I said, it's exactly like, it's just the hierarchy, right? But instead of having to go over here to understand where it is in the hierarchy, you can just pick it at the joint. You can see that one's to there, that one's to there. So, in this case, if I start rotating, it's exactly the same thing. It's just doing a lot of parents together, right? So this one follows that one follows that one, that one follows that one, right? So let's say what I was trying to do was to get that point to 0. You have to kind of work your way down the chain this way. You can also, if you wanted to start to build it up more complex, you can also, say, start there. So I'm going to start over here and build a sort of second chain. And then, because it is literally just a hierarchy, I can pick that joint, and just hit P for parent. And they're now connected. Right? Because it's just graphic. It's just a graphic of exactly the same set of relationships that you would get otherwise. So it's still this is the end of the hierarchy. This is at that point in the hierarchy. Yeah? And that's all, kinematics, they don't render, you don't ever see them in the kind of finished product. They're just controls, right? I mean, it's for making interfaces to complex models. That's all it is. It's just an interface. Where it gets cool is when you start talking, forward is useful for a lot of things, but where it gets fun is dealing with inverse. So I'm going to go back to kind of simpler chain. Let's say I'm just going to do, I'll do that many. So now what I can do, if I look here, that was the joint tool. This is the handle, IK handle tool. I'm going to pick that, and I'm going to pick the end of the chain that I want it to go from, and then to. So now you can see it made this new object called IK handle 1. And when I move it, if physically possible, it solves the rest of the chain to target that point, right? So again, it's this idea of feeding in a position, but solving rotations, right? So again, if you really wanted to, you could sit there and just do the kind of, it's just vector equations. You know, you could solve it if you like, or you can click the tool and let it solve it for you, you know, as you like. And the cool thing is you can also start to layer these things together. So if I wanted to actually just have a second handle that only went from here to here, you know, now I can handle 2. Yeah, all works together. Does funny shit sometimes happen when you get too many IK handles? Absolutely. But here's the other fun thing. So right now, obviously, my wife's car isn't doing very well right now. Must have meant that they didn't think they could fix it. So right now, everything's total free motion, right? So I can move the handles everywhere, and these things are free to rotate in all axes and like however many degrees they want. But what's useful is you can also start to limit that. So if I go to say this joint, I go to the attribute editor, and I go under, there's the joint, and there's the limit information. So let's say I wanted to keep everything where it'll only rotate flat, right? Like you can't get it to twist in this way. So that would mean I only want it to be able to rotate well, it's a little bit off because I didn't make it flat. Hold on, let me do this again so it actually works. So I'm going to turn just the grid snap on. Also, it helps sometimes just to do it in the orthographic view. So if you do it in the top view, you know it'll be flat. So actually, let's do 3. All right, so you can tell that one's right, yeah? So it's rotating in the Y. So what I'm going to do is right now the current is 0. I'm going to hit this little arrow and that little arrow, which sets the min and the max. You can also just turn the whole axis off, but I found that it gives a lot more erratic results. And I'll do the same thing with this one. So you can see it's only Y. So now I'm going to do the same thing. So just making the handle again. Same thing, but now, you know, even if I pull it up, it won't go up there, right? Because I said you can only rotate in this axis. What's useful is then it kind of shows you, is this possible or not, right? I mean, you can give it a target, and if it can't do it, it won't do it. And the cool thing is, you know, you can also here, you know, we basically turn them completely off by saying min was 0 and the max was 0, but of course you can also set that to whatever value you want. So I could say on this one, like after you kind of calibrate through, That's my minimum. And that's my maximum. Actually, I'll say less than that. I'll say like 20. Right, so it gets to that point and it just won't do it, right? Because like with the sort of constraints you set up on the system, it's just telling you, you know what, it's not possible. And I won't go all the way through it just because I don't have it set up right just yet, but obviously these can be useful because what you're doing is it's again setting up a simple input to a more complex system, right? In this case, I'm controlling 3 rotations from 1 input, right? I mean, if I was going to animate this thing, I'm not animating rotations. All I'm doing is animating the position of a target. So 100. You can see it starts to ghost that one in where it's trying to do it, but saying, you know, your system won't do that. I'll key that again. Make sense? So again, it's finding a way to, as these systems get more complex, it doesn't mean that, you know, complex output doesn't necessarily need complex input, right? It's setting things up correctly to run all the time. So, you know, let's say and at the end of the day, you know, each of the joints are just objects, right? So you can kind of connect these values. I usually do it with expression to anything else. So let's just say, you know, we go back to So now we start to talk about real life, right? So, let's say you were going to build this arm out of servos, right? You know, you have, well, you can test in the real world. All right, what is my range of motion, right? How many actual degrees do I get if I tell it 0 and if I tell it 180? Like, how many physical degrees do I get? And one thing I forgot to tell you last time, a way to do that, but I'll give you the key to the world. Speedpaper, right? You poke a hole in it, you put a mark on the servo, you set it to 0. You mark it on here. You set it to 180, you mark it there, and you measure on here how many degrees you've gone. Right? Really simple, but I did a whole project without this stupid things at one time. It drives you crazy because you sit there with a protractor and everything else being like, all right, how many degrees have I gone? And then, you know, one day thought about it and just actually made it out of Matboard the first time. But, you know, when you start thinking about, if I ask you, like on any of these machines, like how many degrees is that servo moving? You would say about this many, right? But the way you do it, and I think looking at that, even with the arm on it, right? You just pop it through here, set it at 0, set it to 180, and measure it, right? It goes 147 degrees or something like that. So then you know, right? So then you know, in my physical world, I have an object that will turn a total of 146 degrees. So then once you know that, you can start to inform the digital stuff, right? You can say, it's a more kind of direct input. Like I know this goes between 0 and 146 degrees, but that means that equals 0 to 180. So if I, for that example, if I look at this joint, you know, I set its minimum to, I'm going to make this a round number so I'll remember it. So I'm going to say the minimum is minus 60. 60, we'll take 60 to 40. So 100 degrees of motion, right? So, and again, you can, once you know the total degrees, that's why these little plastic things are removable, right? You can set your start and end point of whatever that total range of motion is. You just unscrew it, pull it off, and set it. But I know I've got 100 degrees of motion. So from minus 60 to 40. So let's pretend I measured it, right? So let's say I figured out I got 100 degrees total. And I know on here, so when I start to calibrate this thing, that, you know, set it to 0, you know, set it to 0, and this is where it's sitting, and I know that's going to be my minus 60, right? Like if I wanted to make these things match up, like assuming this is your kind of center line, negative 60 degrees. So negative 60 and 40, what I can then do what I'll do first is just connect these two together, right? So in my expression, I will say, actually I'm going to call him servo 1. So I'm going to say servo 1 dot, what is it called, input value? Equals joint dot rotate. So in a very simple sense, what I've done there is simply, you know, is this, oops. It's kind of getting freaked out because the ranges are wrong, right? I know we're outputting 0 to 180, but from my calibrations, I'm not going 0 to 360. I'm going minus 60 to 40. Right? And again, it's a little harder to see because I didn't actually just calibrate it, but so you figure out your limits, right? You figure out your limits and the physical stuff, and then you filter it backwards into the digital. So now, this rotation is being connected and solved back into the sort of calibration of the servo, such that, you know, it's going to rotate the appropriate angle where you could basically match this in real life. And of course, right now you've only done one, and it's kind of pointless to do inverse kinematics with one. But as you might have guessed, today you get additional ones. So you can do the same thing, right? Just say MK servo, rotate Y. That guy is called joint 2. Call him servo 2. Go. And again, I'm copy pasting just because there's less room for error. Edit the expression. We would have to figure out the same thing here then, right? So you figure out your kind of minimum and maximum on the rotations here, convert it to 180. But again, what it means now is you're again pulling one point, and it's solving the multiple ones for you. So I've showed you a couple of examples of when I've used this myself. The easy one example is to see here. Any of those, but this one shows it. Yeah, these are just heavy duty servos. If you notice the little yellow things, this guy, right? Way of calibrating it. I mean, this is using exactly the same plugins you have. So having one handle, move it around, match it up to the servo. And again, all this is done is you just work backwards. So take the physical stuff, figure out its actual range of motion, because physical stuff has limits, right? Digital stuff, you can do whatever you want with it. And you just have to filter the limits back in. And it's the same thing. I mean, that's how these guys work too. Folding the little chair. This was a hell of a lot harder because it's 24 servos off a single Maya model. But again, I should show you this. So we're running, it's 4 6-axis. So yeah, 24, and then one on the table is 25. But again, do you think that I went through and animated 25 values? Absolutely not. It's actually there's one input to this system. So there's a simple, I think I have it on here. Yeah, here it is. This is the animation this was done in the olden days before I figured out how to make it have a kind of real-time link between the two. So all that's really happened to make that work, we worked with these crazy dudes in Vienna who could simulate the mesh going the other way. And in the same way I showed you of like sticking, it's more complex than what I showed you of like, you can stick an object to a surface. Basically I just made a control, made the kinematics, said stick your hand to the surface and follow the normal of the surface. And then all we did was in the single animation of the chair solves all the kinematics, right? So by taking the IK handle and sticking it to the surface, one animation. It's just only the surface, the chair animates, everything else is just linked to it. So again, lots of outputs, so 25 outputs, one input. That's it.
So the servos are just connected to those IK handles and then...
So exactly, in exactly the same system I just showed you. Okay. So each one of those robots is calibrated into the digital one, knowing a kind of minimum and a maximum. These joints are each solving it, right? So this is the problem. Solve the joint. That joint's then linked to a servo, right? You have this much movement and it's been calibrated to be correct. Hit play. The kinematics solve each axis. And this one, it's a bit more difficult because it's actually much more like a CNC machine. This one actually just writes out a huge text file. But instead of like on, if you look at the CNC where it's like XYZ, each line of that one has, that one actually has 28 values because you've got to control grippers and things. But so it's just like a CNC, but imagine 28 values per line instead of 3. So you don't have to get this. You don't have to get to 25 servos just yet, but it's the same idea, right? It's like use the calculation that's built into this thing. I mean, there's a couple of custom tools and a little bit of a tweak to the IK solver on this, but not much. It's mostly just kind of stock animation things. So if the other side of that, as I told you, the other big change between now and 2 weeks from now is everybody gets 2 more servos, right? So going from 1 to 3. Use them wisely. So if you're setting up, as you saw from me, like once you have additional servos, all you do is kind of repeat the process of, pick the object and say MK servo. And so on a software side, before you would go in, get to servo, whoops, that's confusing. There, servo right 1. With all of them, 0 means that's off. Before, or last time I was telling you, you switch it to 1. Well, that is for the first one. For the second one, make it 2. For this one, you make it 3. Right? And there's a lot of other numbers you could choose from, but I would suggest just keeping it that way to keep it simple. Then in the hardware, I'll wire it up here in a second. If you remember, the sort of control pin for the first servo went from 2. It just steps down the line. So the next one's at 3, the next one's at 4, 5, 6, 7, 8. But as I mentioned last time, you can get away with powering one of the little servos just off your USB. Anything above 1, and you'll start to get the kind of over voltage warnings on your USB ports because it's just more power than what it's doing. So what that means is we have to switch to an external power source, which is here, and as you will see, sitting in the chair over there, which is really pretty simple. So where we got to last time, we were previously, well, in this one, on your guys, it's like orange or something, right? So the signal was going off there, and then we were pulling the 5 volts and the ground from the Arduino, right? Well, we don't get to do that anymore. So essentially what you're going to be doing from here on out is the USB is going to be powering the Arduino, and then there's going to be a separate power source that powers all this stuff, right? So as you may have guessed, there's going to be more and more stuff. So it gets its own little power source. So the power supplies you'll be using are like these guys. This is no different than this. Same stuff. This one just doesn't have a cute plastic case around it, which means that it costs about a 1/10 of what one of the other ones costs. These are meant to be like power supplies that live inside of machines, right? What it does mean though is you might want to, like where those screws are, don't jam your finger down in there. Put a piece of tape over it. I didn't do it today, but assume that you're smart enough not to put your finger in an electrical socket. So don't, right? These are live connections, but if you can't figure out to not touch mains power, it's probably evolution at work or something like that. So on the other end, I gave these little things where it's got the little blue connector here. It's just got the 2 pins and it fits into the board. So it just snaps in. Oops. Right. So these guys output, well, between 5 and 6. We can tweak them a little bit. They're probably set to 6 because these things will handle 6. So you'll see on all of these, from the black and white cable, it's split whites positive, blacks negative. So you then just connect them up.
What gauge wire is that? In case we wanted to buy longer.
I couldn't tell you off the top of my head. Small? 16-inch maybe? I don't know. I could tell you if I looked at the thing, but. Again, not the easiest thing to do in the dark. So, it has power, but it's going a little crazy, and I'll tell you why. So the only thing, it's no different, right? Because all we were doing before is just taking 5 volts and a ground plug off of the Arduino. Now I'm just taking 5 volts and a ground from a power source. It's no different, it's just power, right? The one thing you do have to remember, though, is to get things to work correctly, you have to go from the connection of the ground of the external into the ground on one of the ground pins on the board. Because they have to share the ground to be able to communicate correctly. So, right. That works for any of them. Now, it's better to set it up a little nicer. Right? So what it means from here on out is the sort of best practice on this stuff is when you look at the boards, they've got the 2 sets of pins that go down each edge. The kind of nice, clean way to deal with this is so you can come look at it in a second, but basically what I've done is instead of going straight to the servo, I connected it into one of these pins down the side. And where the ones in the middle run this way, these run the other way around. So it basically means that this whole row of red now has 5 volts and the whole row of blue is ground. So then I can just jump off of there. Right? So for the next one, if I had these guys, so I'm going to plop the servo down the board. This one, again, this one's white, red, black. White's the signal, red's positive, black's ground. So first things first, move it over here so it's easy to get to. So I know from the code that it's going to be servo 2. Servo goes to the 2, goes to the next pin there. Yep. So now all it needs is power. All of these are power, so I just literally plug it in. Again, I'm doing this quickly and not paying much attention to the length or the color. The more organized you are, the better. So take that one to power. These guys aren't so you can see. So, right. So now I've got 2. Yep. And again, it's just a sort of, however many you add, it's always the same idea. There's always a kind of there's 2 wires that are just power. So the positive, like 5 volts on the ground that you plug into what will now be the external power source. And the third one that is the sort of information signal. And, you know, in theory, with this sort of system, I mean, you could, well, like I said, I've done 28 servos at once, because it's just modular, right? As long as the power source can power them all, which these can handle as many as you want. It's just about chaining them together, because it's just a signal, right? Because it's not a lot of information. You're literally feeding it a couple of numbers per thing, so it's pretty robust. And, you know, I'm showing it this way. You know, you don't need to make it with like little arms or kinematics, but, you know, you could rotate each one individually. You know, this is another kind of fun thing. I'll go back to the beginning here for a second. So actually in this, I'm going to do it slightly differently. So, before I had said constrain all the axes, but that's not really what I want this time. I don't really care about the twisting. So I'm actually only going to constrain y and z. So I'm going to go here, here, check that, say y, z. So again, right now, I just said, damn it, I picked the wrong ones. Let's try this again. So here, here. Maybe it's X and Z. So Z. Doesn't make any sense. No, that's right. So then what I really want to know let's get it close enough. So we'll relate it to the X rotation. And again, if you imagine this, if you start from the sort of physical world and work backwards, and again, if okay, I have about, if you say 180 degrees, right? Right, I have 180 degrees of motion, but from where to where, right? You can kind of choose what that range is. Is it from here to here? Is it from here to here? You can pick those things. But the cool thing is, once you kind of know that, so let's say I know I have 180 and I want it to go from here 180 this way. So right now it's going to go from, well, we'll say it goes from 26 to then 154. Yeah, 154. No, or does it go to negative? No, it's going to go to negative. So it means 26 to minus 140. Anyway, it doesn't matter. So the cool thing is, like I showed you with the joints, you can actually do that with anything. So I can take this guy and on the cone and not the shape, if you scroll down, there's limit information and then rotate. So we'll just set it this way. So I can say that's its maximum. Click it on. That's its minimum. Click it on. So again, just like before, I can go outside of it, but it knows the sort of limits of the system. And you could also then, what's that about? And then, could connect them together. So then I'm just going to say oh yeah, that's the other thing that's interesting about constraints is you can start to unlike the previous things where it's a kind of one-way street, you know, I can move this thing. I can move the cone just as much as I can move the sphere.
If you animate the rotation on the cone, will it move the screen?
No, because what the constraint controls is the rotation, right? It controls the rotation. You can control anything but the rotation. So what I'm doing is controlling its position. The node is calculating the rotation. Anyway, so again, I'm going to call this guy servo 1. Say servo 1 dot ly equals. What's that? Oh, sorry. That's not true. I want to say servo 1 dot input value.
Cone
And this one's already been set. Oh, it's because,
You looked it up before the last.
yeah, I need to hit the range again. So minus 46 to 21. So then I need to filter that in of minus 26 to 1, right? And that's why it's made that way, because you're always going to get these weird actual angle ranges in your model versus, you know, what exists in real life. And what this little panel does is calibrate the two together. So, but I did it totally half-assed here, so it may not be working.
You linked it to cone 2 instead of
It was code 1 set there too. Should come to.
Thank you. Right, and again, this is just showing you. I won't go through it here. You could set up, you know, if you wanted two of them looking at pointing from two different places, right? You could, again, link this one. And then and again, you'll notice you keep things with similar names so you can copy and paste. So I'm going to go here and attach it to the correct output by saying servo number 2. Oh, shit. Hold on. Let me remake this. Accidentally turned it into a subdivision service. Also, if you're wondering how I did that, after I typed mkservo once, and until you close Maya again, you can use the up and down arrows, and it'll tell you the last commands you've put in. So just by hitting the up arrow, it brings it up. So So because I deleted the object, it deleted that part of the expression before. And now I go here. Oh, I haven't calibrated the second one with the right range of values. But you get the idea. Again, making the rotations the kind of output of a more complex system. I'm not rotating them. All I'm doing is moving something and telling it, look at that object. So